we've learned that the directional derivative, the derivative of f in the direction of u evaluated at p naught, is the gradient vector evaluated at p naught dot the vector u. For simplicity, in this video, we'll just refer to that as del f dot u and agree that I'm evaluating del f at the point p naught. So, now that I know my directional derivative has this dot product formula, there are a couple neat things we can conclude. Because I know a dot product is also the magnitude of the two vectors multiplied together times the cosine of the angle between the two vectors. So I'm going to make a note here that theta is the angle between the gradient vector and u. And again, though I'm not saying it, I'm thinking about evaluating del f at an actual point p naught and that unit vector u. But wait, the unit vector u is a unit vector, so this is just the magnitude of del f times cosine of the angle between that unit vector and del f. Okay, well, cosine has natural bounds. Cosine's always between -1 and 1. So now I know that at that point p naught, the largest value my directional derivative can ever be is the magnitude of the gradient vector. And I know exactly when that happens. That happens when cosine is equal to 1, which happens when the angle is 0. So, my directional derivative is equal to the magnitude of del f when the direction vector u and del f have the same direction. So the magnitude of del f is the largest my directional derivative can ever be. And that happens precisely when I'm pointing in the direction of del f, where u, my direction vector, points along the vector del f. This tells me a neat thing. The vector del f points in the direction of most rapid increase. So, if I have a surface in the domain and if I have a function z equals f of x, y, and I take a point, p naught, and I calculate del f at that point, literally pointing in the direction that the surface increases the fastest. Well, that's really cool. So while we're thinking about that directional derivative, being equal to the magnitude of del f times cosine of the angle between u and del f, I can also figure out the direction of most rapid decrease. The smallest value this directional derivative could ever take on is the opposite of the magnitude of del f. And that occurs when, well, theta is equal pi. Because that would mean I would need a -1. So cosine pi is -1. That's where I get that minus magnitude of del f. So del f points in the direction of most rapid increase. That's a 180-degree turnaround. So the direction of most rapid decrease is going the other direction. That's literally minus del f. So del f points in the direction of most rapid increase, and minus del f points in the direction of most rapid decrease. But maybe the coolest thing of all is what happens right in the middle. If we think about what happens at theta equals pi halves, a direction orthogonal to the gradient vector? Well, cosine of pi halves is 0. That's a direction of 0 change. Any direction u that is orthogonal to del f is a direction of 0 change. Well, it's worth noting too that if I think of pi halves being one way and 3 pi halves being the other way, the cosine of 3 pi halves is also 0. So I end up with the same conclusion. So del f itself points in a direction of most rapid increase. The opposite of del f points in a direction of most rapid decrease. And the vectors orthogonal to del f point in a direction of 0 change.